Good morning. Thank you, Anne, for that introduction. As Anne mentioned, I am the latest chair for the CPD committee, so I'm glad to see, as Anne mentioned, a great turnout here today. Here it's actually close to 250 people attending throughout the day, which is a great number. And Anne mentioned I'm here to keep you in line. Really what I'm here to do is whatever Rosalie tells me to do. Those of you who know Rosalie, Anne, she's done it. It's really the brains behind this whole endeavor. But I've been with the CPD committee for a few years, and we've made a lot of great strides, and I've heard some positive feedback, and I'm glad to see this day come to fruition. One thing I want to mention, a couple of housekeeping items, is I have this clipboard with everyone's name on it, and a little checkbox. It'll be passed around over the next short while, and please check off that you are here, and if you do check off, you get automatically credited for these events towards your continuing professional development hours. That's a good thing. You'll see these in the other rooms too. After 10:15, we're going to do some breakouts into other rooms, and you'll see these clipboards being passed around. So make sure you get a handle on those and check off your name. So we have a couple of presentations coming up. They're half hour each, and I'm not going to spend any more time talking about the event, but let me first introduce the City Tar Ponds presentation. The first two presenters or presentations are both awarded Lieutenant Governor Awards of Excellence. This first one on City Tar Ponds, we have with us Bruce Noble, who is the Director of Remediation Services in ACON, and he'll be joined by Dan McDonald, who works for CDCL, and is also one of our councillors here in Nova Scotia. So without further ado, I'll ask those two gentlemen to come on up and start the presentation. Thank you.
We're pleased to be here to make this presentation. I made it here a couple of years ago. The project was still in this finishing up now, but now it's done. And just to start off, the AECOM CBCL team were the engineering team that did all the pre-engineering, the engineering, and the construction management. Bruce is going to co-present with me today. Bruce and I were heavily involved in the engineering side of it, and that spilled into the construction management too, but we're also fortunate to have our project manager, Ray Rice, here, who was sitting out there somewhere, Ray. Anyway, we're pleased, we're going to have to say everything right, because Ray may jump up if we do something wrong. But anyway, we're going to I'm going to do the first part of it. The last time I was here, I did the whole presentation, so you're lucky this year here I'm only doing half, and Bruce is going to do the other half. What I'm going to focus on is the years leading up to the remediation. And it was certainly interesting times, and then Bruce is going to focus on the actual engineering of how it went on. So I'm just going to start off with a brief history of the Sydney Steel Mill, the tar ponds, and the coke ovens. Okay, this is the future land use and sustainable remediation. This picture, whoops, go back here. This here shows the stabilization solidification when it was in full operation in the project, so Bruce is going to elaborate a little more on that. This is just a general overview of Cape Breton Island, showing some of the highlights, and Cabot Trail, and Nottingmaster, Lewisburg, and why it was so important to clean up Sydney in order to enhance the rest of the island and the beauty that's there. So there it is. The steel plant began in 1899. It began construction. It was the largest North American steel mill in 1901, and in 1912, the steel mill was producing half the steel made in Canada, and what's not up there, it was about 30% of the steel made for World War II effort too in Canada. So it was a major contributor to the Canadian economy, to the war effort and everything. It has a lot of historic significance. Interesting thing, this picture shown here, this picture wasn't 1912, this picture was 1971. So, that's what it looked like when I grew up. And story there, when I came home from St. Halifax, I was 19 years old, and the drinking age had just started, so the best dance in Sydney was Thursday night at the Pure Legion, Starlight Room was called. But you learned very quickly you couldn't wear a white shirt, because you couldn't get from the car to the thing there without being covered with orange ore dust, and that's a true story. So it's you had to wear dark clothes because of the ore dust. There it is, 6,000 people at its peak. And there, in this picture here, again, this picture is the coke ovens here that generate the coke. Steel plant is in the background, Sydney Harbour's there. This picture was taken in 1987, 1 year before the coke ovens closed. So It hasn't been that long ago since it was a major polluter. There's some of the facts. 100 years of coking operations. The tar ponds is 81 acres. There were 700,000 tons of contaminated PAHs and 45,000 tons of PCB contaminated sediments. The coke ovens site is 178 acres, 3,000 tons of PAHs and VOCs, contaminated soil, and 25,000 tons of coal tar in a tar cell. Up until 1958, the tar that was a byproduct of making coke was sold. It was the Dom tar bought it, and in 1958 they stopped. So I think that's when most of the problem started with the tar ponds, is they just started dumping the tar into the brook, and then eventually they created a tar cell, which was just an unengineered landfill. They dug a hole and put the tar in it. So that's what we were facing with at the start of the job. There were 2 failed cleanup attempts. In 1991, which was probably the first time I worked on the project in a very minor role. I was a structural designer and designed the bins for the fluidized bed incinerator. That failed. One of the reasons what happened there was that they did not find, in the initial characterization of the tar ponds, they did not find the PCBs. The incinerator was basically built for $51 million when they discovered the PCBs. There's a major public outcry that the incinerator couldn't burn PCBs. That was correct. I talked to some experts who said it could be modified for another $10 million to do it, but by now the public outcry was there, and the whole $51 million thing was scrapped and subsequently demolished. So now with that failed attempt, they came on. There's the incinerator. There's the tail end of Sydney Steel comes over here. That was a sludge delivery line that was going to be dredged up from the tar ponds and delivered via line to the incinerator here. That line failed engineering-wise too. It didn't work, and the dredge failed. The dredge was trying to dig up the sediments, and it kept getting tied up. And the thing that really got the dredge tied up was all the Sobe shopping carts that were thrown into the tar ponds. And the cutter heads got wrapped into a shopping cart. They just destroyed the cutter head. So it failed. It failed politically. It failed engineering-wise, and it was a failed attempt. The second one was this here is the big slag pile from Sydney Steel, 7 million tons of slag. And in 1994, the decision was made, and they started the engineering, which wasn't much engineering, was to push all this slag into the tar ponds. And that came with another major public outcry that we're just going to bury it and leave the contaminants and no remediation, and through the public intervention, that one failed. So then the government decided to do something, so they formed the Joint Action Group, which was called JAG. And that was, it was federal. There were 3 levels of government signed an MOU. The federal government, the provincial government of Nova Scotia, and the regional municipality of Sydney signed an MOU, and Ottawa, Nova Scotia, they put $62 million into a cost-sharing agreement for scientific studies, pre-engineering, all that kind of stuff. JAG formed a roundtable. There were 39 people on the roundtable from various things. They formed working groups. Every Monday night, the engineering group met. Tuesday night, the health and safety group met. Wednesday night, the social economic group met. And at the end of the month, they all reported to the roundtable. Now, the roundtable, I'll say that this was, and the thing was, the federal government and the provincial government said they would pay for the cleanup, but now they wanted consensus. So you had 39, and consensus meant they want 100% agreement from roundtable. Now, I'll be quite frank, there were 39 people at that table that couldn't agree on what type of coffee to order. I presented way too many times to that thing that I want to remember. There were union leaders there, there were construction companies there were government officials there were concerned citizens there, and there were environmental activists there. They were all on the roundtable, got appointed, and it was just, I mean, there were nights the police came and to break up what's going on. So, as much as it was well mentioned, I think the lesson learned here that consensus was impossible. So JAG went on for 5 years with these roundtable meetings every month, and more information and some engineering studies done, and I presented some of them there. So the purpose was to identify, like I said, identify the potential solutions. So back in 2000, our firm, CBCL, won the what's called the RARE, Remedial Actions Evaluation Reports. And we identified 6 possible cleanups for the Sydney tar ponds and 4 for the coke ovens. Now our mandate there, so you can see what we were supposed to discuss, the description of the cleanup technology, the construction methodology for doing it, the order of magnitude, costing, conceptual schedule, economic benefits. But the main thing is, you see there, we were not to select an option. We're only to present the facts in our study. This cost this much, this took this long, this is what the benefits would be. Then JAG took that, provincial government hired some kind of management, public relations consultant, and they developed a workshop and workbooks. And they brought in, the nurses union, medical, teachers, people off the street, concerned citizens, and they all had a vote on the cleanup. And at that time, we were looking at the recommended one was to stabilize and solidify the ponds, cap the tar ponds, but to incinerate the PCBs. So with that being voted on by the people and selected by the government, then we move forward, with that to the preliminary engineering. And that's AECOM and CBCL won that preliminary engineering, and we looked at the ones that were selected, the stabilization, the solidification, the impact assessments, and Bruce is going to explain all that when he gets up. Incineration of the PCB impacted sediments, final capping, and then for the coke ovens, it was an interceptor barrier, and Bruce will explain that, groundwater collection, surface cap, and final, which Bruce will go into a bit of detail on the engineering on those. So once that happened, we were able to move on and get the preliminary engineering. And then, but before they moved on to the final engineering, there were 4, in that 62 million, there were 4 projects that were called preliminary remedial works, which were done, and they were done to get ready for the big major project. So Coke Ovens Brook was contaminated, so we built a new line brook around it, so when the remediation came, we could go clean. The old one was decommissioned. So one of the things was to relocate the coke oven brook that went right down the center. The second thing was we had a city water line running through the coke ovens, and we were just fortunate it never got a leak, and it leaked all those contaminants into the water going to Whitney Pier. So, and then Battery Point Barrier, you'll see in the pictures that Bruce has, Mugger Creek, as it's called, was where the tar ponds were. And then there was a mouth where the mouth went out into Sydney Harbor. So we determined to clean up the tar ponds, we had to cut off Mugger Creek from the ocean, basically. So, and there was a second reason there too, besides the technical reason, was that under the laws, Ocean Dumping Act, Canadian Dredging Act, all that sort of stuff, if we didn't cut it off, it would be considered still part of the sea and subject to some very onerous and long regulatory approvals, which we already had a pile of long regulatory approvals. So we cut it off for a technical reason, and for the other reason to say, all right, we've isolated this body of water, so now we can go clean it, and it's no longer part of Sydney Harbor or no longer part of the ocean from I guess, a regulatory point of view. There's Battery Point Barrier right here at the mouth. We had to leave a small discharge area, which we eventually closed off. I forgot one, the cooling pond. Sorry, I forgot one, the cooling pond. The fourth one was the cooling pond. Now here's the tar ponds in here, right here. The cooling pond was a man-made pond for Sydney Steel that when they quenched the steel rails with water, the water picked up a lot of heavy metals, some hydrocarbons. So then the water was circulated there to cool. So it would cool, and then they could recirculate it for cooling the next batch of rails. But subsequently, over the years, it settled out with a lot of heavy metals and PAHs. So the cooling pond was, we were doing that first, the CBCL team, and that one was designated, and it wasn't what they call a First Nation set-aside, it was the First Nations capacity building. So we negotiated with 3 First Nations contractors in the area to divvy up the work. One was doing the stabilization solidification, one was doing all the pumping, and the other one was doing sort of the treatment stuff anyway, and trucking in of the materials for the capping. So our team were hired to work with them. So we actually supervised, we took people and trained them how to do water sampling, we trained them how to do stabilization, solidification, we trained them in general health and safety, construction health and safety. And I guess this was deemed a very great success, especially by the federal government, because those contractors were able to bid on the open market and secure jobs in open competition on the tar ponds after they were trained by this cooling pond First Nations capacity building. And there's I talked about, there was the brook alignment. Right here, we realigned the brook, the old one was coming down through here, and there was the relocated water line that we took out of the coke ovens and put down the Main Street, Victoria Road. So this is the legacy, 100 years of, I mentioned before, coking operation, steelmaking, tar ponds, 81 acres, 750,000 tons of contaminated sediment, coke ovens, 178 acres of soil groundwater. And at this point in time, I'm going to turn it over to Bruce to tell you how we did it. So that was sort of the history building up to when we started, and Bruce will take it from here. Thank you.
Thank you, Dan. Let's see. This way. Okay, so this slide just shows a general overview of the infrastructure that was installed, the remedial efforts that were advanced to clean up the site, the coke oven site and the tar ponds. So I've got a lot of slides. I'm going to move pretty quickly. And there is some kind of engineering slides, and there's some other non-engineering focused slides which I think we think are important to point out. So in the foreground is the coke ovens site here. That was capped in its entirety. Coke oven brook in blue, that was the conveyance of the contaminants from the coke oven into the tar ponds. That was all reestablished and lined, and a groundwater collection system installed. That groundwater was pumped to a water treatment plant here, and these black lines, some cut-off walls to manage groundwater, both clean coming onto the site and ensure the contaminated water was not migrating off-site, but rather to the groundwater collection system. The tar ponds are in the background, and they appear small, but as Dan mentioned, they're about 85 acres. So these were solidified and stabilized and then capped. And two surface water bodies, and I'll show some slides in a minute that talk about the pumping operation, Coke Oven Brook and Wash Brook. They were pumped around during the execution of the stabilization component, but in the final condition, those brooks needed to be allowed to flow through into the ocean as they did previously through the tar ponds, but in the final condition through some engineered channels. And so that gives you a good kind of overview of the combined solution. So we started the engineering in 2006, scheduled fixed end date completion by 2014, and we were actually complete a little bit early. The stabilization and solidification, in order to complete that work, it's very important to control water. You're basically adding cement powder and other aggregates to solidify, strengthen the material, and lower the hydraulic conductivity of the material. So control of water was paramount. The picture in the top left is a good shot. Dan mentioned the battery point barrier and controlling ocean. So that's actually steel sheet pile, discharge structure, and barrier combined function, holding back the ocean while we're doing stabilization, solidification in the tar ponds in the deep water condition. This sediments were stabilized and solidified in situ, which means they weren't moved somewhere else and stabilized and then put back. It was all done in situ, and they were capped with a soil and engineered cap post-treatment. So through the engineering process and design, we went through a number of steps and stage-gated regulatory approval at each step in order to advance the design and confirm that the conditions of approval from the EA panel would be met, and that as it was scaled up from bench to pilot and from pilot to full-scale construction, the criteria that had been established could be met and ensure that we had confidence at each step. Dan mentioned the failed attempts earlier, and the stage-gated kind of approval steps were in place to help prevent a similar situation. So these are the three criteria that were established to measure success of the stabilization effort. So strength, and to support the cap primarily, reduced hydraulic conductivity by 2 orders of magnitude. So 10 to the -6 centimeters per second was the final goal. And leachability, and we had two test methods to test leachate coming off of the stabilized material to make sure that the contaminants were bound up as we thought they would be, and as the bench and the pilot predicted they would be. So I mentioned water control, and just briefly, we did it in stages. So we established in stage 1, on the bottom end of the picture, 2 pumping stations at Washbrook and Cokeoven Brook. They would pump the surface water around and as well de-water the ponds. And in the normal flow condition, the flows were rather moderate and manageable, but in a high flow condition or rain event, the catchment was an urbanized catchment, and the flows could increase dramatically, orders of magnitude. So the pumping capacity of these pump stations was about 14,000 liters per second. So you can see a picture of the pump station in, I think that's stage 2, on the right-hand side of the foreground there, and you can see that the engineered channels that I mentioned that would eventually convey that surface water through the site in the final condition. You can see those channels in the background, and I applaud the engineers that restrained themselves from designing straight-line brooks and having a little meander in there, so that's nice to see. Data management and quality control and assurance of quality on that quality control was a big deal. It was a deliverable to our regulators to prove that we had done what we had said we would do, to prove compliance with the contract. And it was also a big deal because we had 700,000 tons of sediment, and we were testing every individual 200 cubic meter, 300 cubic meter cell that was treated. So we ended up with over 3,000 individual cells, and each cell had all the performance-based criteria for leachate strength and permeability. It had geomatics information. It had QA and QC. It all had to be geo-referenced, because once you assessed and the test results came in a week, 4 weeks, sometimes 56 days later, you had to be able to go back and say, this was a failed test in this exact area, and we need to retreat if that was the case. So it was a big deal, and there was a lot of effort to coordinate between our team and the Stantec independent QA team, as well as the contractors, Norlease, that were implementing the work to make sure that the quality control report that was delivered at the end of the job, we were able to check that box. Odors ended up actually being a bit of a surprise. Everybody knew from years of planning and the tar ponds being in the middle of town that odors were an issue, especially on a hot summer day, and especially when the tide was out. And so we had a plan to manage that, and what we found is that plan was insufficient when we got into the first kind of full year of construction. And the South Pond was totally dewatered, and they started mixing up these sediments, and the wind was blowing in the wrong direction, and we got quite a few complaints. So a number of things were done to ensure that it was done without impact to the community. And I should mention these, there is a very big difference between odors and emissions. So emissions were tested and regulated. We had criteria at fence line and within the community to manage and control emissions. That wasn't the issue, it was nuisance odors. And so we developed, with the contractors, with the owner, an odor management plan. We implemented odor suppression and odor control with various foams and another product called Rusmar. And the complaints dropped off. The owner, Sydney Tar Ponds Agency, established a 1-800 kind of odor hotline, advertised it on radio and in the papers, and if folks had an issue, they could call this number, and a representative from the project team from the owner was there to address that issue. But it was successful, and spent a lot of money on foam and different color foams, made all kinds of for all kinds of interesting remarks. But but it was a successful program. Only issue and lessons learned was it was successful with an initial kind of misstep and initial complaints in that first full season. The remaining 2.5, 3 years that we implemented it, it was successful. So I'm going to talk a little bit about green and sustainable remediation, and there are 3 pillars to GSR, and I'll get to those in a minute. This is maybe what I would say is more the kind of the non-engineering aspect of the presentation. Future land use was discussed long ago, and there were studies done, and while the engineering was advancing, people were also talking about what the project would be after the remediation was complete. And so there was some interesting ideas. A report, as I said, by Kistics was done, I believe, in the late 2006, 2008 timeframe. And that report, I think, for what I understood or for what I could see, kind of sat on a shelf for a little while, and maybe it was just because we were so focused on the engineering and getting to construction. The other aspect of GSR is benefits to the local community. So there's economic aspects to that. There's also social benefits to that. So there was a local economic benefits requirement within our contract, within every company's contract that worked on the project, to report what their contract benefits, direct and indirect, were to the local community. So in a community that had seen coal mining go away and the steel plant shut down, a major employer, and the governments were going to come in and spend $400 million to clean up their town. The obvious reaction and desire was to have as much of that money spent locally as possible. So I think this was a huge success, and by many different measures, a huge success. Not just the CDCL team, but all companies, and there were very many companies that worked on the project in reporting and allowing the owners to document the benefits locally on the economic front. So I guess the social model, or the social aspect of GSR, to me, I, to be quite honest, didn't pay a whole lot of attention to it, and I probably had a hard time defining it if somebody asked me. And I didn't grow up in Sydney. I moved there from away in 2006, but when I moved there, I could see the signs that said incinerator with a line through it, and you knew that there was an impact of this site on the community. And this picture in the bottom right, I think you saw it before on one of the slides, came through my inbox on a Friday afternoon in the fall, and I think it was 2011. And the title of the email was "The Ponds Go Green," and I just, a whole bunch of images or memories kind of came back, and I thought, oh wow, this is great. This is impactful. This is something that the community can see as progress. And it was really the start of some changing and thinking for me personally, and some kind of light bulb moments that remembering back into the engineering design when Dan and I were poring over plans and building specs, and our original project manager was talking about Coke Oven Brook, and the kids would go fishing one day in Coke Oven Brook when we're all done here. And I kind of thought he was a little bit out in left field, but this was the start of my kind of changing my thoughts around what that meant, especially to the community. So you can see that the site was drastically transformed between 2008 when construction started and 2013 when it's almost done here in the bottom right picture. And this is me up in the top left in 2005 in full tie-back and duct tape around my boots and respirator and face shield, taking samples for our bench scale and preliminary design. And this is the world-class playground that's probably 400 feet away from that spot where I took those samples in 2005. And the last thing I was thinking of in 2005 was a playground, kids playing on top of the ponds. I was thinking, this stuff really stinks, and wow, is there ever a lot of it? So 10 years can really change things. I think this is kind of good. It shows a progression of the site from open to the ocean and dewater to bottom left, SS complete cap not quite done but almost done, and then future land use, grass and trees. And, you know, they opened the park in 2013 to the public, and it was a huge turnout. They made paid homage to the coal mining tradition, the steel, the history of steel making. It's called Open Hearth Park. So the city Tarpon's name is banished forever. We should rename this presentation, Dan, for the next one. And they had concerts and they had fireworks, and I think the year later they had an Aerosmith concert. So this one here is something, when we were doing research for this presentation, that really caught my eye. So I was having a hard time envisioning what the site could be or would be. And 5 years before I ever even heard about the Sydney Tarpons, was grade 5, I believe, grade 5 class. I was asked the question, what would Sydney be if the Tarpons were gone? And they got it mostly right. They had parks, they had fishing, they had bridges, and they had playgrounds. And when you're thinking about, I guess, engineering, and when you're thinking about science and making sure that the solution is going to work, I would encourage you to also think about what it means to the community, and I would also like to point out that what we build and what we do, and not just cleaning up contaminated sites, goes far beyond engineering and science. And Dan was telling me this morning at breakfast that last Saturday he was headed into town to watch Dartmouth come and play football on the field, and the bleachers were full. They should have built the bleachers bigger, and they've got hundreds of people watching these football games. And not just that, but there's 50 kids on this playground, and there's another 100 people doing walking around the trails. And anyway, it made me feel pretty good, and I think the community has really embraced what the park is now, and it's a pretty good legacy. I'd encourage you to all go have a look at it if you get the chance next time you're up in Cape Breton. Thank you very much.
Thank you, Bruce and Dan, for that presentation. A little thank you for attending and presenting this topic to Bruce and Dan. It's a little donation to the May Best Memorial Scholarship Fund on our behalf. Thank you. Okay, we're going to quickly transition to the next presentation. And I see nobody has signed off on the sheet yet. What's up with that? That's because it's here and I left it here. So you have half an hour, the next half hour, pass this around quickly and find your name and check off. I'll make sure to take that back. Two quick things I want to mention about that presentation that rang true to me. I can infer from Dan's comments, he's from Cape Breton, as am I, and I grew up in the better town of New Watford. Anyway, that orange smoke comment rang true to me. I remember being a kid and driving through Whitby Pier and being enveloped by that dense orange smoke and thinking how cool it was as a kid. And subsequently realizing that it wasn't so cool.
One thing, my father drove the buses in Waterford for 27 years.
Yeah.
And I can remember going through where you used to have to put the wipers on and it wasn't raining just to get the ore dust.
Oh yeah, it was thick. And the other thing I'll mention is I have 2 young kids now, and I go back to Cape Breton quite often, and that playground is in fact pretty cool. Both my kids love it, and we go there every time. So it's a great project, thank you for that. Another comment I need to make is to move people to the front if you're standing. There's lots of room. I'm up here. It's a good place to be, so come on up front, there's room up front to sit. And without further ado, I'm going to move on to the next topic, which is, again, Lieutenant Governor Award project. David Bulger and Alice Cumming, both from SNC Lavalin, are structural engineers, and they're going to present today about the Halifax Library, which we all are well aware of. So I'd like to welcome them now and carry on. Thank you.
Thanks, Christian. Good morning, everyone. I'll stop my water here. My colleague Alice Cumming and I are going to talk a little bit about the new Halifax Central Library. SNC Lavalin was one of the project team members that designed the library, where we provided the the leads for both the civil and structural engineering. Has anybody had a chance to visit the library? Yeah, quite a few. So the site, as you may know, is right here at the corner of Spring Garden Road and Queen Street. But this new Halifax Central Library is not the first building that was on that site. In approximately 1801, Bellevue House was constructed by the British Army and served as the residence for the commanders-in-chief while they were stationed in Halifax. And Bellevue House stood there until it was demolished in approximately 1955. So the story goes that the gardens on the property of Bellevue House were so impressive in the spring of the year that that's where Spring Garden Road got its name from. So the construction phase of the project started with an archaeological dig. And you can see here some of the Bellevue House foundations are uncovered. And so there's all sorts of interesting things found, including pottery and jewelry and an old fireplace hearth and different things like that. So while this was going on, Spring Garden Road, of course, is right here. The construction for the foundations for the building were going on over to the side here. So this archaeological excavation kept us from being able to move forward on the property for a few months through the summer until it was complete. This is an image of a scale model that was prepared by the architects and presented at one of the public meetings. And this is around the time that we kind of fully realized how much trouble we were in structurally as far as challenges to solve. Here's a shot of the excavation of the bedrock in the footprint of the library. Spring Garden Road, of course, is up here. And we've excavated approximately 5 meters of bedrock to get down to a level low enough to be able to get a parking garage in. And then we see workers installing pad footings, and pad footings, of course, are below the level of the slab on grade for the parking garage as well. So we're down here quite a ways, as you can see, lots of rock movement. One of the tools that we used for design and drawing preparation was we built this is the early stages of one of our BIM models. This is a Revit model in the early stages. So to help with to try and get a sense of how much rock was to be excavated, we took our Revit model and superimposed a bedrock surface in the model. So this bedrock surface we prepared from both geotechnical results and topographical surveys. So from that combination, we were able to get a pretty good handle on how much rock had to be excavated from the property.
Here you can see another print from the 3D structural Revit model. Building information modeling was used by structural and civil design disciplines and allowed for the close coordination between other design engineering disciplines. 3D structural analysis software was used for the design of a number of structural elements, including the building shear elements, the cantilever truss, the various stair trusses, and pedestrian bridges. Lateral forces on the building are resisted by 4 reinforced concrete cores, making up the elevator and staircase cores. Detailed 3D structural analysis was completed to model the shear cores under a number of load cases and combinations. The cores are sized to resist the worst case of wind, seismic, and notional horizontal loads. The cores themselves cantilever vertically from the basement level, where they are supported by concrete pad foundations. Floor diaphragms at each level connect to the shear walls by embedded steel plates. The use of shear core elements enabled the extensive use of glazing and curtain walls around the perimeter of the building. The perimeter walls were not designed to contribute to the lateral rigidity of the building. A cantilever truss structure structure on the 5th floor overhangs the building towards Spring Garden Road with an overhang of approximately 9 meters. Architectural requirements meant that the space was to have glazing on 3 sides to allow for a panoramic view of the Citadel and Spring Garden Road. A veer-and-wheel truss style, by definition, does not have diagonal bracing. This truss type was selected to maximize the view on all sides of the space. Rigid moment connections are provided at each node to give the structure lateral rigidity. 3D structural analysis was completed and considered numerous load cases and combinations, including wind pressures, wind uplift, seismic, dead loads, live loads, snow loads, and temperature effects. Limiting deflection and vibration was important for both serviceability reasons as well as for connection of glazing. The truss was cambered for dead load. Now we'll return to the construction sequence. Here you can see the placement of concrete at the parking level slab on grade. Here you can see the pumper truck and concrete truck working together. This slide shows the shoring and scaffold system that was used for forming the elevated cast-in-place concrete floor structures. This shoring system enables partial removal of support posts as they are no longer required for supportive construction loads. The system is lightweight and easily removed for reuse. This photo shows the top side of the shoring and scaffold system panels. The aluminum beams and posts are seen below. A one-way slab and band beam system was selected during design as opposed to a two-way slab system to accommodate the heavy unbalanced floor loading. At this location, the drop panel provides formwork for the band beam. The higher panels provide formwork for the underside of the one-way slabs. Reinforcing steel projects from the top of column at this level. Beam reinforcing ties to the top of column at this location. You can see it here and beyond. This photo shows placement of reinforcing steel at a section of the main level structural slab. More congested reinforcing steel can be seen in the background at the beams and shear walls. Now back to Dave.
We had a number of structural challenges. The main part of the building was reasonably straightforward. It had a pretty consistent grade. The bulk of the building is cast-in-place concrete. But at the south end of the building, where what we now have is the performance space, which is this area in here, the architects and the owners wanted a large open space for performance. So the normal building grid would have allowed us to have a column just here and here where these shoring posts are, but after going through a number of options, it was determined that those columns were not going to be allowed, so we had to take them out. So we ended up with two sizable cast-in-place post-tension concrete beams. So you can see one just here and one here. So these beams are approximately 4 feet wide and approximately 6 feet deep and span about 18 meters. This is a shot of one of the beams before concrete was put in the formwork. You can see that it's comprised of conventional reinforcing, but you can also see the conduit here, which creates a void in concrete to be able to put post-tensioning strand in. This is our drawing that shows the design of it and what's meant to be constructed. So the conduit that we just looked at in the last slide makes a void in this draped shape throughout the length of the beam. So that creates a void. We cast concrete in the formwork, and then we fit post-tension strands into that voided space. And here you see the strands after being installed are being tensioned by 2 workers with a monostrand jack. So we tension one strand at a time, Each one of these heads has 27 strands in it, and there's 2 groups of strands per beam. So this is one beam here, and you can just see beyond the tail of the other beam. So the sequencing for tensioning these is basically going back and forth to have a balanced tension load. This is another shot from our Revit model. It's the south part of the building, and again, you can just see the post-tension beams, one here and one here. And on those beams are level 2, level 3, level 4, and the roof. So there's approximately a 4,000 kilonewton point load comes down on the midspan on those 2 beams. So that was we spent a fair amount of time trying to get that just right. Here we have a shot of one of the steel trusses at fabrication. This is Cherubini Metalworks Fabrication Shop in Burnside. This is one of the 2 cantilever trusses. The members themselves are box shaped, but they're made completely out of plate, steel plate, welded together. So we ended up with this sort of scenario to satisfy both ourselves structurally and the architects for open space and visual aesthetic. This is the same truss after it was delivered to site. Looking down on it from up in the library. The trusses are fabricated completely in the shop, but then they were cut in half to be able to ship from the shop to the site. So the truss is about 8 meters or 24, 25 feet high, but they were cut in half just here and just here, and then welded back together in the field. So here you can see a guy, I guess he's on his back there, doing a full penetration weld in the field. This is the leading edge of the elevator core. We have some significant steel plate cast into the concrete, which we use to anchor the back of our cantilever trusses back to. So up here you can just see some connection detail. And this is a close-up of a lower connector that's will help to hold the bottom core of the truss in place. Here we have the crane hoisting the first truss into place and holding it there while workers work at a man basket to install connection bolts. So they're working at that top connector at the moment. And here we see both trusses installed with some of the 4-beam steel going in. And this shot kind of gives you a bit of perspective on the height where, compared to these 2 workers, it's quite a tall space. Here we have a profile of the steel as it projects out towards Spring Garden Road. This space, I guess, has become known as we call it the Halifax living room. And so it cantilevers approximately 9 meters past the point where it leaves the building to the leading edge. And this is essentially the entire makeup of the steel framework that supports the this cantilevered Halifax living room. 4 beams, roof steel is in there, all the girts, and there's some planning basin as well. Here we have basically the entire framework for the building. As you probably have seen, the bulk of the building is actually cast in place concrete with feature steel elements. And workers installing curtain wall after the structure is fairly well complete at this stage. And these are our famous Harry Potter stairs. There's 4 stairs and 3 bridges that kind of meander the way up through the atrium space to get you up into the different levels. And you can just see up top some of the framework that supports the skylight. There's 23 structural steel moment frames that help support the glazed monument skylight. And here we have opening day. There's approximately 20,000 people visited the library on opening weekend. And seems to have been very well received since it opened. There it is, New Halifax Central Library.
Thank you, David and Alice. Again, here's a token of appreciation and thank you for making us excellent college fun. Thank you for that. So we're running just a bit early, which is not a bad thing. I don't know if all coffee's here yet, but we're heading up into our coffee break. The coffee's going to be just in the hallway, right? Yeah. So the next phase of our day is right around 10:15. We're going to split into one of three different rooms. This one being the main room, we also have room 204 and 205. All right. Change the slide, oh, it's on the slide. There it is. There's where the next events are happening. And that was just one thing that made me think when, that last slide when you showed the opening day when there's 20,000 people. One of the benefits of being an engineer is that sometimes we get sneak previews. And I know that there was an arrangement done. I actually attended the site visit prior to opening, which was kind of nice. So we always want to keep guys up with those events. One of the perks of being an engineer. All right, so everybody has some coffee, enjoy, have a chat with each other, and rejoin at 10:15 and we can back in rooms. Thanks.